Welcome to a short lesson over the intermediate value theorem. Our objectives for this lesson are to define the intermediate value theorem, describe a real-world context whereby the intermediate value theorem applies, distinguish between situations where we can and cannot apply the intermediate value theorem, and prove that a zero exists in a certain interval using the intermediate value theorem to support your argument. To help you to get an idea of what the intermediate value theorem is, I'm going to go over a scenario with you. So let's say that I'm driving along the road and I look at my speedometer and I notice that I'm going 50 miles per hour. So at time A, I'm going 50 miles per hour, and I'm going to plot that here on my graph. Then after some time has passed, I notice that I'm going really fast. So again, I look at my speedometer and I'm going 100 miles per hour this time. So at time B, I'm going 100 miles per hour. So my question then is, how do I know that I was at some point between time A and time B driving at 70 miles per hour? Well, to increase my speed from 50 miles per hour to 100 miles per hour within time A and time B, I had to have somewhere in between gone 70 miles per hour. And it doesn't matter which way I went. For example, let's say I take this path. Let's say that I'm speeding along and I shoot up past 100 miles per hour, and then I see a cop, and then I start to slow down very quickly. That's one route. Or let's say I take a more direct path. So it doesn't matter which way I choose to go. Well, 70 miles per hour would be about right here. So if I choose the first path, notice that I do hit 70 miles per hour right here. And so that's going to be at some time between point A and point B. Let's just call it C. And if I take the more direct path, notice I also hit 70 miles per hour between 50 miles per hour and 100. It's just at a different time that happens. And we'll just call this time D. So let's look at an example of a path that I could have taken where I would hit 70 miles per hour more than once between times A and B. So I start out at time A and I shoot up past 70 miles per hour, and then I slow down to about 65 miles per hour, and then I speed up past 100 miles per hour, and then I slow down until I get to time B. Let's look at all the points where we hit 70 miles per hour. So I have this point here. And we'll call that time C. And then I hit 70 miles per hour at a different time here. And we'll call this time D. And then I hit it at one more time over here. And we can call this time E. This scenario just shows us that if I'm driving along and within times A and B, I go from 50 miles per hour to 100 miles per hour, then at least one time between times A and B, I will be driving at 70 miles per hour. In the previous slide, we showed that if a car is driving along the road and it increases its speed from 50 miles per hour to 100 miles per hour between times A and B, then there must exist some time C between times A and B such that the speed of the vehicle is 70 miles per hour. So keeping that scenario in mind, let's go over the intermediate value theorem. So we have theorem 1.13, the intermediate value theorem. If f is continuous on the closed interval AB, f of A is not equal to f of B, and k is any number between f of A and f of B, then there exists at least one number C in the closed interval AB such that f of C equals k. So in the scenario that I just showed you, f was just the function that described the driving path that we took. And we know that we can't jump from one speed to another speed, so f is continuous. In my example, that's just all of the times between 50 miles per hour and 100 miles per hour, including the time that we're at 50 miles per hour and the time that we're at 100 miles per hour. And if you notice, 50 is not equal to 100, so we've met the condition that f of A is not equal to f of B. And then we have the condition that k is any number between f of A and f of B. And so I chose a number between 50 and 100, and that was 70 for 70 miles per hour. Then the conclusion we can draw is there is at least one number C in AB such that f of C equals k. So for our example then, there is at least one time C in the closed interval of time A and time B such that, so f of C just means that the point on the curve at time C. So when we say f of C equals 70, what we're saying is that somewhere along the curve created by the driving path, at time C, the speed is 70 miles per hour. So what I just showed you was a very specific example where we use the intermediate value theorem and we didn't even realize we were using it. But the theorem is very useful in mathematics. What it does is guarantee the existence of at least one number C in the closed interval AB such that f of C equals k. And as I stressed earlier, that's going to be at least one number C in the closed interval AB. And this just lets you know that there's a possibility that f of C equals k for more than one C. And you can see that in the graph here. For C1, C2, and C3, notice that they all equal k. Something else that needs to be stressed is that the intermediate value theorem requires that the function must be continuous. And we can look at this graph here to understand why. So notice we have a closed interval AB. Then if you look on the y-axis between f of A and f of B, notice that we have k. But because the function's not continuous, there is no function value f of k on the graph. So if we were to try to use the intermediate value theorem to come to the conclusion that there's a C such that f of C equals k, well then we would be making a mistake because we would probably assume that it's at this C right here, but there is no function value there because there is a gap in the graph. The graph is not continuous. So you can see why we have the condition in the theorem that the function must be continuous. If it's not continuous, we can't use the intermediate value theorem. Let's look now at a graphical example of the intermediate value theorem. Here we have the function f of x equals negative x plus 2 times x minus 1 squared. We are asked to plot a point on the graph above the zero and a point below the zero. And notice our zero right here in bright blue. So let's first pick a point above the zero. So why don't we do this one? That point is approximately It looks like negative 2.22. So let's write that down. And then let's just pick any point below. So right here. That point is approximately negative 1.9, negative 1. So we'll write that down. So what do you notice about the 2 points? Well, I don't know if you noticed what I wanted you to notice, but what I wanted you to notice was that the y values go from positive to negative as we move across x values. Or in other words, f of negative 2.2 is greater than 0, and f of negative 1.9 is less than 0. Because the graph is continuous between x equals negative 2.2 and x equals negative 1.9, and the y values change from positive to negative, we know that there must be some x equals c such that f of c equals 0. Because in order to get from positive to negative, you have to cross 0.